The oldest light in the universe holds secrets that could rewrite our cosmic story. This is the cosmic microwave background, a fossilized afterglow from the Big Bang itself. But this ancient glow is not a simple picture. It is a cosmic detective story filled with perplexing puzzles. We are still piecing together the clues hidden within its subtle patterns. By the end of this journey, you will understand 25 of the most compelling mysteries that make this faint whisper of creation the most important map in cosmology. Why does this light appear to point in a specific direction, challenging a fundamental law of physics? And what is the true nature of the bizarre cold spot that some scientists think could be a bruise from a collision with another universe? What do you think is the most profound question we can ask about the cosmos? The uniformity of this ancient light presents our first great cosmic puzzle. Look at the map of the cosmic microwave background. No matter which direction you point your telescope, the temperature is almost exactly the same, a near-perfect 2.725 degrees above absolute zero. This seems natural at first glance, like a cup of coffee cooling evenly, but the cosmos is not a simple cup. According to the standard Big Bang model, the universe was not old enough at the moment this light was released for heat to have traveled from one side to the other. Think of two people standing at opposite horizons, too far apart to have ever exchanged a shout or a signal, yet they are both wearing identical clothes down to the same thread count. This is the horizon problem. Regions of the cosmos on opposite sides of the sky were forever separated by a particle horizon, a boundary beyond which no influence could possibly reach. They were cosmic strangers, yet they share an identical temperature. How could they have coordinated this perfect uniformity without ever communicating? The leading explanation is a dramatic event called cosmic inflation, a period of faster-than-light expansion in the universe's first fleeting moments that stretched a tiny, connected patch into our entire visible cosmos. But here is the catch. While inflation elegantly solves the problem, we have no direct proof it occurred. It remains a compelling, yet unverified idea. So the horizon problem stands, a foundational mystery written in the universe's oldest light, challenging us to explain how the cosmos achieved its perfect thermal harmony. This perfect uniformity is not the only strange coincidence. The geometry of our universe itself presents a second great riddle, one that speaks to a truly improbable balance at the dawn of time. The cosmic microwave background reveals that our universe is flat. This does not mean it is a two-dimensional sheet like a piece of paper. In cosmology, flatness describes the large-scale geometry of space itself. Think of it as the fabric of reality having zero overall curvature. A flat universe is the ultimate tightrope walk, a perfect equilibrium between the outward rush of expansion and the inward pull of gravity. If the universe had possessed even a tiny bit more matter and energy, that extra gravity would have caused space to curve in on itself into a closed sphere, eventually collapsing in a big crunch. If it had possessed just a little less, space would have curved outward like a saddle, flying apart into an ever colder, emptier void. For the universe to be as flat as we observe it to be today, its initial conditions in the first fraction of a second had to be balanced on a razor's edge of unimaginable precision. The required fine-tuning is staggering. If you compared the universe's initial expansion energy to its gravitational energy, they had to match to within 1 part in a trillion trillion. That is like balancing a pencil on its tip for billions of years. Any slight wobble, any deviation from this perfect balance would have been magnified exponentially over cosmic time. A universe that was just slightly curved at the beginning would be dramatically, unmistakably curved by now. The fact that we see a flat universe today means it must have been almost exactly flat at its birth. This is the flatness problem. Why was the cosmos set up with such an impossibly perfect, fine-tuned initial state? once again, the theory of inflation is called upon to provide an answer. The idea is that this period of hyper-expansion would have stretched the fabric of space so violently that any initial curvature would have been smoothed flat, just like blowing up a wrinkled balloon makes its surface appear flat and smooth. But this just pushes the mystery one step further back. What physical process could have triggered such a monumental event, and why did it stop? The flatness we observe remains a profound clue, pointing to a moment of cosmic calibration so precise it defies simple probability. This fine-tuning of the cosmos extends to the very particles that should have been forged in the fiery dawn. Grand unified theories, our most ambitious attempts to describe nature's fundamental forces as one, make a startling prediction. In the extreme heat of the universe's first moments, a special kind of particle should have been created in unimaginable abundance. These are magnetic monopoles. Think of a magnet you might hold in your hand. It always has both a north and a south pole. You can break it in half, but each new piece will instantly form its own pair of poles. A magnetic monopole would be a fundamental particle that is just a north pole or just a south pole all on its own. According to the physics that describes the early universe, these exotic particles should have been as common as protons. They are incredibly heavy and stable, meaning they would not have decayed. They should still be here today, all around us, a dense relic sea of these cosmic curiosities. Yet, despite decades of searching with incredibly sensitive experiments, not a single confirmed magnetic monopole has ever been found. They are utterly absent from our observable universe. This is the mystery of the missing monopoles. Their absence is a deafening silence, a major clue that our picture of the universe's earliest moments is incomplete. These particles would have been created right around the time the energy source for the cosmic microwave background was being set, making their predicted presence a direct challenge to our models. So where did they all go? Once again, the theory of cosmic inflation offers a compelling solution. The idea is that the same violent, faster-than-light expansion that smoothed the universe also diluted the density of these monopoles. Imagine you had a single grain of sand in a small box. That is a high density. Now imagine that box suddenly expands to the size of our entire galaxy. The grain of sand is still there, but the chance of you ever finding it becomes virtually zero. Inflation would have stretched space so dramatically that any primordial monopoles were scattered so far apart that their average density dropped to effectively zero in our visible cosmos. They are still out there, perhaps, but lost in a universe grown impossibly vast. This elegant solution, however, comes with a caveat. The monopole problem is now a key piece of evidence for inflation, not a settled matter. We have not found the monopoles, and we have not yet found direct smoking gun proof for inflation either. The missing monopoles stand as a ghostly testament to a revolutionary event we can only infer, a cosmic cleanup of monumental proportions that left behind a universe curiously free of these predicted fossils. But what if the universe itself has a preferred direction? Deep within the faint temperature variations of the cosmic microwave background, some researchers believe they have found a spine, a strange alignment that has earned a dramatic nickname, the axis of evil. This is not an axis of moral corruption, but a potential crack in one of cosmology's most cherished foundations. The cosmological principle states that the universe on the largest scales should look the same in every direction and from every location. It should have no center, no edge, and no preferred direction, a concept known as isotropy. The axis of evil suggests otherwise. It refers to an apparent alignment where some of the largest fluctuations in the CMB, the biggest hot and cold spots, seem to be coordinated along a particular line through space. Imagine looking at a map of the world and noticing that all the tallest mountain ranges and the deepest ocean trenches inexplicably line up along a single, straight line running from the north to the South Pole. That is the level of strangeness we are talking about in the cosmic map. This alignment seems to point in a specific direction, as if the universe has a subtle tilt or a fundamental handedness we never anticipated. The debate over this anomaly is fierce. Is it a real feature of the universe, or is it just a statistical fluke, a pattern our brains are imposing on random noise? The data is incredibly subtle, and the statistical significance is a battlefield for cosmologists. Some analyses claim the alignment is too strong to be a simple coincidence, while others argue that when you look at any complex dataset, you are bound to find some seemingly odd alignments if you search hard enough. It is the cosmic equivalent of seeing a face in the clouds. The real problem is that if the axis of evil is real, it forces us to question the cosmological principle itself. Our entire understanding of the universe's evolution, from the Big Bang to the formation of galaxies, is built upon the assumption of isotropy. A universe with a preferred direction is a universe that is fundamentally different from the one we thought we lived in. Could this axis be a shadow of something from before the Big Bang, an imprint from a larger multiverse? Or is it a mere illusion, a cosmic mirage that will vanish with more precise data? For now, the axis of evil remains one of the most tantalizing and controversial ghosts in the cosmic machine. This strange alignment is not the only anomaly that defies easy explanation. Far across the cosmic map lies a region so profoundly cold it has sparked debates about parallel realities. Known simply as the cold spot, this vast area in the cosmic microwave background is significantly chillier than our models say it should be. It is not just a little bit colder, it is a colossal patch of sky, a cosmic cold front spanning nearly 1 billion light years. If this temperature dip were caused by a random statistical fluctuation in the primordial plasma, the odds would be astronomically low, like rolling a die and getting the same number 100 times in a row. So what could cast such a long, cold shadow across the oldest light in the universe? One leading explanation is the supervoid hypothesis. Imagine a region of space that is not just empty, but profoundly, abnormally empty, a cosmic desert where galaxies and dark matter are strangely scarce. As light from the cosmic microwave background travels through such a void, it must climb out of this gravitational well. This effort saps its energy, stretching its wavelength and making it appear colder to us, an effect known as the integrated Sachs-Wolf effect. It is like a photon losing steam as it climbs a long, gentle hill. The search for this proposed supervoid, however, has yielded conflicting results. Some surveys suggest there is a corresponding underdensity of galaxies in that direction, but it does not seem large enough or empty enough to account for the profound cold we observe. The void, if it is there, is not void enough. This mismatch has led scientists to consider far more exotic possibilities. The most staggering idea is that the cold spot could be a cosmic bruise, a remnant of a collision with another universe in the vast multiverse. In this scenario, our infant universe, during its early inflationary expansion, may have bumped into a neighboring bubble universe. The energy released in such a colossal impact could have left a distinct, cold imprint on our cosmic microwave background, a scar from a long-ago encounter with a reality entirely separate from our own. This is, of course, a highly speculative idea, but it highlights just how desperate cosmologists are to explain this anomaly. The true nature of the cold spot remains one of the most captivating open cases in modern cosmology. Is it a rare but natural fluke in the cosmic tapestry, a simple void we do not fully understand, or is it our first tantalizing piece of evidence for a cosmos far grander and stranger than we ever dreamed? The cosmos feels strangely quiet on its grandest stage. When scientists examine the largest possible patterns in the cosmic microwave background, they find a silence that is just as puzzling as any anomalous signal. This is the mystery of the missing large angle correlations. The temperature fluctuations we see are not completely random. They are connected with hot spots and cold spots influencing each other across the sky. On small and medium scales, these correlations follow a predictable statistical pattern. like the consistent rhythm of ocean waves. But when we look at the very largest scales, spanning more than 60 degrees across the sky, this rhythm falters. The correlations between these colossal features are significantly weaker than our standard models of the universe predict. It is as if, on the biggest canvas imaginable, the universe ran out of paint. These large angle correlations are not minor details. They are the imprints of the very first seeds of structure, the primordial ripples that would one day grow into the vast cosmic web of galaxies and clusters. The fact that they are fainter than expected suggests that something fundamental may be missing from our story of those first moments. One profound possibility is that this statistical quietness is a clue to the actual size and shape of all reality. Our observable universe might be just a small patch of a much larger and possibly finite whole. Imagine living in a vast but enclosed hall. You would never see patterns larger than the hall itself. The largest waves you could observe would be limited by the walls around you. In a similar way, if the entire cosmos is not infinite but has a complex, finite shape, like a three-dimensional torus or a twisted maze, it would impose a maximum scale on the correlations we can observe. The patterns would simply have no room to express themselves on scales larger than the universe itself. This would mean the cosmos is not an endless void, but a contained structure with a definitive, albeit unimaginably large, geometry. Alternatively, this lack of correlation could be a statistical fluke, a rare quiet patch in an otherwise noisy cosmos. Or it could point to a more exotic beginning where the process that generated the initial ripples, perhaps during inflation, operated in a way that suppressed the very largest waves. Whatever the cause, this large-scale silence forces us to question the most basic assumptions about the arena we live in. Is the universe truly infinite, or are we just perceiving a finite fragment of a grander, more intricate design? The answer is written in the quietest part of the ancient sky. This cosmic conspiracy runs even deeper than a single axis. The plot thickens when we examine the specific patterns or moments that make up the universe's largest structures. Scientists break down the CMB map into components called multipoles. The quadrupole and the octopole are the first two of these complex patterns beyond the overall average temperature. The quadrupole represents the most basic stretched-out deviations, a kind of cosmic lopsidedness. The octopole is the next level of complexity, a more intricate arrangement of hot and cold spots. According to our standard model, these patterns should be oriented randomly, scattered across the sky with no particular relationship to one another. They should be like two different sets of fingerprints from two different people, completely unrelated. But the data tells a different story. The quadrupole and octopole are not just aligned with each other, their planes and hotspots seem to be coordinated. Even more bizarrely, their alignment also appears to match the so-called axis of evil. It is as if the universe's largest features are all whispering about the same secret direction. The statistical odds of this happening by pure chance are incredibly low. This is not just one anomaly, it is a chain of them, a pattern within a pattern that points toward a fundamental strangeness in the cosmos's architecture. So is this a clue to new physics, a flaw in our measurements, or the universe's most unlikely coincidence? One possibility is a systematic error, some unknown contamination in the data. Perhaps our own galaxy's foreground light is subtly influencing the maps in a way we have not fully accounted for. Yet, multiple satellites from WMAP to Planck have seen hints of this alignment, making a simple error less likely. If it is real, the implications are staggering. It could mean that the seeds of all cosmic structure were not perfectly random. The process that generated the initial ripples, perhaps during inflation, may have had a preferred direction baked into it from the very start. This would challenge the core principle of isotropy at a level even more fundamental than the axis of evil alone. It suggests the universe might have a primordial handedness, a spin on the grandest scale that we are only just beginning to perceive. The aligned quadrupole and octupole remain a quiet but persistent hum in the data, a cosmic whisper that the largest things in existence might all be pointing toward the same unknown truth. The universe seems to prefer one side over the other, as if the cosmic map of creation were painted with a heavier hand in one half of the sky. Scientists have uncovered a startling imbalance known as the hemispherical power asymmetry. When they analyze the fluctuations in the cosmic microwave background, they find that the power, the overall strength and variance of those hot and cold spots is not evenly distributed. One celestial hemisphere appears to have more vigorous, more pronounced fluctuations than its opposite. It is as if you were listening to a symphony and realized all the violins were playing louder on the left side of the concert hall than on the right. This discovery did not come from a single eureka, a moment, but from a careful statistical sifting of the data from missions like Planck. Researchers divided the sky into two halves and compared the statistical properties of the temperature variations in each. The difference was subtle but statistically significant, a persistent whisper in the data that something was fundamentally lopsided. This finding strikes directly at the heart of the cosmological principle and its assumption of isotropy. If the universe is truly the same in all directions, why would the very seeds of structure be planted more densely in one particular half of the cosmos? One of the first and most straightforward explanations to consider is our own local motion. Our solar system, our galaxy, all of us are moving through space at a significant fraction of the speed of light. This movement could, in theory, create a Doppler-like effect, stretching the light in one direction and compressing it in another, making fluctuations appear stronger in one hemisphere and weaker in the opposite. It would be like running through a rainstorm, feeling more raindrops hit your front than your back. Yet, when scientists meticulously correct for this known motion, a significant portion of the asymmetry stubbornly remains. It seems this cosmic lopsidedness is not just a trick of our perspective. This points to a far more profound possibility that the asymmetry is primordial, baked into the universe from its very first moments. Perhaps the process of inflation, the event that supposedly smoothed the cosmos, was not perfectly uniform itself. It might have had a gradient, a slight slope in its energy field, causing it to stretch one part of the infant universe with a different intensity than another. This would have imprinted a fundamental handedness onto the fabric of reality, a legacy of uneven expansion written into the first light. The hemispherical power asympathy forces us to ask whether the Big Bang was perfectly symmetric, or if the cosmos was born with a subtle but undeniable tilt, a cosmic preference that has shaped everything we see from the very beginning. Peppered across the vast, smooth canvas of the cosmic microwave background are tiny, sharp pinpricks of intense temperature. These are the point source anomalies, and they are the cosmic equivalent of finding unexpected faces in a crowd. They are not the broad, gentle hills and valleys of the primordial fluctuations, but sharp spikes, like a single bright star against a dark sky. The problem is they should not be there. These point sources are far smaller and hotter than the background itself, and they do not match the profile of any known astrophysical object. They are not distant galaxies, nor are they the glowing dust of our own Milky Way. When scientists meticulously subtract all known sources of foreground contamination, from quasars to radio galaxies, these stubborn dots remain. They are identified through intense statistical filtering, searching for pixels in the colossal data map that are too hot and too concentrated to fit the standard model. The great challenge is separating a true cosmic signal from the countless layers of interference. It is like trying to hear a single, unique whisper in a roaring stadium. Every instrument has its own noise, its own quirks, and the data processing required to clean the CMB map is unbelievably complex. Could these anomalies be the faint echoes of cosmic strings, hypothetical defects in space-time left over from the early universe, lines of immense density that could focus CMB light into sharp points? Or are they evidence of primordial black holes, tiny remnants from the Big Bang itself, whose evaporation could leave a distinct mark? Some researchers even speculate about entirely new classes of objects, cosmic phenomena we have not yet dreamed of. The hunt to explain them is a painstaking process of elimination, a forensic investigation on a cosmic scale. Are these point sources the first hints of new physics, or are they simply the last, most subtle artifacts of our own imperfect measurements? Their resolution requires ever more sensitive eyes on the sky, instruments that can stare deeper into the ancient light and finally decide if these cosmic specks are fundamental flaws in our understanding or just dust on the lens. Beyond these strange points and asymmetries lies a deeper layer of perfection, one that presents a mystery in its very flawlessness. The spectrum of the cosmic microwave background is that of an almost perfect blackbody. Imagine the pure, clean light emitted by a theoretically perfect object, one that absorbs all radiation that hits it and re-emits it with a precise, smooth distribution of colors. The CMB's light matches this theoretical curve with astonishing fidelity. This near perfection is itself a powerful confirmation of the Big Bang, but cosmologists are now hunting for the tiny, expected imperfections in this perfect curve. These are the spectral distortions, minute wiggles or bumps superimposed on that smooth blackbody spectrum. They would be the faintest of echoes from colossal cosmic events. A spectral distortion is like a single wrong note in a perfectly tuned symphony, a subtle scar hinting at a violent interruption in the universe's calm infancy. These distortions would not appear as hot or cold spots on a map, but as a specific warping of the light's energy across different frequencies. Finding them would be like detecting the unique chemical signature of a fingerprint at a cosmic crime scene. What could have left such a mark? The most tantalizing possibilities involve immense injections of energy into the primordial plasma. Vast populations of primordial black holes evaporating in a brilliant flash could have done it. Or perhaps exotic particles of dark matter, finally decaying after eons, released a burst of power that heated the cosmic soup. Even the slow dissipation of sound waves from the formation of the very first structures could have generated a specific type of spectral distortion. Each proposed cause would leave a different fingerprint, a unique shape in the distortion that would point directly to its source. So why have we not found them yet? The challenge is one of unimaginable sensitivity. The distortions are predicted to be incredibly faint, buried deep within the signal, far below the noise level of our current telescopes. It is like trying to hear the flutter of a butterfly's wings from a mile away during a hurricane. Our magnificent observatories, like Planck, were designed to map the temperature variations, not to detect these exquisitely subtle spectral warps. The hunt requires a new generation of purpose-built instruments, experiments designed not to look at the sky, but to listen to it with a precision we have never before achieved. These next-generation detectors will operate at the extremes of cryogenics, cooled to a fraction of a degree above absolute zero to silence their own internal noise. They will measure the absolute intensity of the CMB light across a wide range of frequencies, searching for those telltale deviations from perfect blackbody radiation. The quest for spectral distortions is a search for the ghosts of cosmic cataclysms, events so powerful they left a permanent scar on the light of creation, yet so subtle we are only now building tools delicate enough to find them. Hidden within the faint temperature map of the cosmic microwave background is a second, even more subtle layer of information, a secret message written in the very orientation of its light. This is polarization, and its most elusive form holds the potential to confirm our grandest story of creation. To understand it, think of light as a wave rippling through space. Normally, these waves vibrate in all directions perpendicular to their travel. But when light scatters off particles like the electrons in the primordial plasma just before the CMB was released, its waves can become preferentially aligned, like a crowd suddenly deciding to wave their flags in the same direction. This is polarization. Scientists categorize these polarized patterns into two fundamental types, E modes and B modes. E modes are the simpler, curl-free patterns. They are like the radiating lines you see around a magnet or the gentle gradient of a hill, and they are primarily created by the density fluctuations of ordinary matter in the early universe. We have already detected these E modes, and they beautifully confirm part of our standard model. But B modes are different. They are the curl patterns, the ones with a handedness, like the swirling water going down a drain or the intricate loops of a fingerprint. Most B modes we can observe are generated later in the universe's history, created as the CMB light is gently warped by the gravitational pull of intervening galaxies and dark matter, an effect called gravitational lensing. The real prize, however, is something far more ancient and profound, primordial B modes. These would be a direct imprint of gravitational waves generated in the first infinitesimal fraction of a second after the Big Bang, during the theorized period of cosmic inflation. Inflation would have stretched quantum fluctuations in the fabric of spacetime itself into macroscopic gravitational waves, ripples in reality that would have left a unique, swirling signature in the polarization of the CMB. Finding this specific B-mode pattern is the holy grail of cosmology, a direct glimpse into the universe's first moment of existence and the ultimate validation of inflation. The challenge of this hunt is almost beyond comprehension. The predicted signal is incredibly faint, a whisper buried beneath a mountain of noise. The biggest contaminant is our own Milky Way, which is filled with swirling clouds of interstellar dust. This dust is not only cold, it is also magnetically aligned, and it emits its own polarized light that perfectly mimics the swirling pattern of the primordial B modes we are desperate to find. Separating the cosmic signal from this galactic foreground is a monumental task, requiring exquisitely sensitive telescopes observing at multiple frequencies to map and subtract the dust's contribution. This immense difficulty has led to both high drama and deep controversy. A few years ago, one team made a stunning announcement claiming they had detected the primordial B-mode signal. The excitement in the scientific community was electric, a potential Nobel Prize-winning discovery. But further analysis revealed a heartbreaking truth. The signal they saw was almost certainly contaminated by galactic dust. They had been fooled by the cosmos itself. This experience taught us a brutal but necessary lesson about the challenges of this search. The hunt continues today with ever more sophisticated experiments located at the driest, coldest places on Earth, from the high Chilean deserts to the South Pole, all straining to hear the faintest echo of spacetime's first shudder. The search for primordial B-modes remains one of the most ambitious quests in science, a patient, meticulous effort to read the universe's very first signature. The universe's first light also holds the key to its first chemistry. Just minutes after the Big Bang, the cosmos was a searing nuclear forge, an era known as Big Bang nucleosynthesis. In that brief, intense window, the first atomic nuclei fused together from a soup of protons and neutrons. The amounts of hydrogen, helium, and a tiny trace of lithium that were created in those first moments were set in stone by one crucial number, the density of ordinary matter, or baryons. This is where the cosmic microwave background provides an exquisitely precise measurement. By analyzing the subtle clumping in the CMB, scientists can calculate the universe's baryon density with incredible accuracy. It is like using the echo of the birth cry to weigh the very stuff of stars. This precise measurement from the CMB allows us to run the clock backwards, to simulate the conditions of that first nuclear furnace with unprecedented confidence. The predictions for the amounts of deuterium and helium match what we observe in the oldest corners of the universe almost perfectly. But there is one glaring exception: lithium. The CMB data, combined with our standard model of particle physics, predicts a specific amount of lithium-7, the light element's stable isotope that should have been forged in the Big Bang. When we look at the ancient stars in the halo of our galaxy, stars that are made of nearly pristine material from the early cosmos, their lithium abundance is only about 1/3 of what our theories say it should be. This is the lithium problem, a mismatch that has persisted for decades. It is not a small error, it is a factor of 3 discrepancies staring back at us from the oldest stellar fossils we can find. So where did the lithium go, or was it never made in the amounts we think? Perhaps our understanding of the nuclear physics in that first fiery minute is incomplete. Could exotic particles from the dark sector have interfered with the fusion processes, altering the final yield? Or is it possible that the surface of these ancient stars is not a perfect time capsule, that some process over billions of years has slowly dragged lithium down from the surface into the stellar interior, hiding it from our telescopes? The lithium problem is a quiet but profound crack in our otherwise successful story of the universe's first few minutes. A reminder that even with a perfect map of the ancient light, the earliest chapters of cosmic history can still hold onto their secrets. Our cosmic map reveals a universe expanding at 2 different speeds. This is the Hubble tension, a crisis born from the conflict between how fast the cosmos grew in its infancy and how fast it is flying apart today. The cosmic microwave background provides our most precise early universe measurement. By studying the subtle patterns in this ancient light, cosmologists can calculate what the expansion rate should have been 13.8 billion years ago, and then use our standard model to predict what that rate must be today. This CMB-derived value is exquisitely precise, yet when astronomers use modern techniques to measure the current expansion rate directly, by observing the distances and velocities of nearby stars, supernova, and other cosmic markers, they get a different answer. The universe now appears to be expanding significantly faster than the ancient light says it should be. The discrepancy is not a small rounding error. It is a stubborn, statistically significant gap that has persisted through years of ever more careful measurements, now standing at a confidence level of about 5 sigma. In the world of physics, that is the threshold for a genuine discovery, not a fluke. It means there is only about a 1 in 3.5 million chance that this tension is a simple mistake. So why does the young universe's story contradict the old universe's reality? One possibility is that we are being fooled by unknown systematic errors. Perhaps our methods for measuring cosmic distances today contain a subtle, unaccounted for bias, a consistent misstep in our cosmic yardsticks that makes nearby galaxies seem farther away, and thus the expansion faster than it truly is. Yet, as different teams using different techniques continue to confirm the faster modern rate, this explanation becomes harder to sustain. If the error is not with our measurements, then it must be with our model. The standard model of cosmology, known as lambda CDM, might be incomplete. Perhaps the early universe contained additional types of radiation or exotic, fast-moving particles that subtly altered how the CMB looks, tricking us into calculating a slower predicted expansion. Or maybe dark energy, the mysterious force driving the acceleration, is not a constant as we have assumed. What if its strength has been increasing over time, giving the expansion an unexpected extra push that our models did not see coming? The most profound resolution would be a modification to Einstein's theory of gravity itself on cosmic scales. The Hubble tension is more than a numerical puzzle. It is a direct challenge to our understanding of cosmic evolution, forcing us to ask if we have truly grasped the forces that have shaped our universe from its first whisper to its present rush. This invisible cosmic architect shapes everything we see. While the cosmic microwave background is a map of light, its deepest story is written by something that emits no light at all, dark matter. The patterns in that ancient glow, the precise sizes and distributions of the hot and cold spots, could not exist without the gravitational pull of this mysterious substance. Think of the early universe as a vast sea. The ordinary matter, the protons and neutrons that make up stars and planets, was like a thick syrup, constantly pushed and pulled by the intense pressure of radiation. It could not easily clump together to form the seeds of galaxies. Dark matter, however, was different. It was an invisible anchor, a ghostly skeleton unaffected by light's pressure. It began to collapse under its own gravity first, forming vast, unseen wells of potential. The ordinary matter then simply flowed into these gravitational potholes, pooling there until it was dense enough to ignite into the first stars. The CMB shows us the blueprint of this process. The statistical signature of the temperature fluctuations is a perfect match for a universe where dark matter outweighs normal matter by a factor of 5 to 1. Without this dark scaffolding, the cosmic structures we see today would simply not exist. Yet for all its profound influence, the CMB tells us virtually nothing about what dark matter actually is. It confirms the presence and the weight of the shadow, but not the substance of the shadow itself. Is it a sea of undiscovered particles, a trillion times lighter than an electron washing through the cosmos? Or is it a population of primordial black holes, forged in the first chaotic second of the Big Bang? The CMB data rules out some of the most extreme possibilities, but the fundamental identity of this cosmic ghost remains one of the greatest puzzles in all of science. The next generation of CMB observatories will hunt for more subtle clues. They will search for tiny, secondary signals that could reveal how dark matter particles interact with each other or with ordinary matter, even in the most minuscule ways. They will look for the faintest imprints left if dark matter decays or annihilates, events that would have injected a whisper of energy into the primordial plasma. The hunt is to move from knowing the shadow is there to finally glimpsing its true face. But the invisible anchor of dark matter is not the only ghost in the cosmic machine. A second, even more mysterious force is at work, one that the cosmic microwave background reveals not by what it builds, but by what it prevents. This is dark energy, the enigmatic driver of the universe's accelerating expansion. The story of its discovery is written in the faint echo of the Big Bang itself. When scientists use the CMB to measure the total density of the universe, they get a very specific number. We know from the CMB's patterns how much of that density is ordinary matter and how much is dark matter. But when you add those two components up, they account for only about 30% of the total. The remaining 70% of the cosmos is something else entirely, a smooth, persistent energy that seems to be woven into the fabric of space itself. This is the dark energy budget, a number the CMB provides with stunning precision. Yet for all its quantitative certainty, the CMB tells us nothing about what this energy actually is. It is like being able to read the total on a restaurant bill with perfect accuracy, but having no idea what any of the individual items were that you ordered. The primary candidate is the cosmological constant, an idea that Einstein originally proposed and then discarded. This suggests that empty space itself has a fundamental energy, a constant push that causes the expansion to accelerate. If this is true, dark energy is simply a property of the vacuum, unchanging and eternal. But there are other, more dynamic possibilities. Perhaps dark energy is not a constant, but a cosmic field that has been slowly evolving over billions of years, its strength waxing or waning. This would mean the acceleration of the universe is not a permanent state, but a phase in a much longer story. It could grow stronger, ultimately tearing apart galaxies, stars, and even atoms in a final big rip. Or it could fade away, allowing gravity to one day regain control. The most radical possibility is that dark energy is not a form of energy at all, but a sign that our understanding of gravity is fundamentally wrong on the largest scales. Einstein's theory of general relativity, the foundation of modern cosmology, may need revision when applied to the entire cosmos. The CMB acts as a crucial referee in this debate. Its precise measurements of the distance to the last scattering surface provide a fixed ruler against which we can test these ideas. By combining the CMB with other probes, like the distribution of galaxies or observations of distant supernova, we can trace how the expansion rate has changed over cosmic time. So far, the data is consistent with a simple cosmological constant, but the uncertainties are still large enough to allow for more exotic explanations. The true nature of dark energy remains the most profound puzzle in cosmology, a mysterious force that determines the ultimate fate of everything, yet whose identity is completely unknown to us. Our universe may have been born with a magnetic personality. Woven into the fabric of the cosmos from its very first moments could be vast, primordial magnetic fields. These are not the familiar fields of stars and galaxies, but something far more ancient and fundamental, stretching across the entire universe. Their existence is still a profound mystery, and the hunt for their ghostly signature is focused squarely on the cosmic microwave background. If they are real, these fields would have been present when the CMB light was first set free, and they would have left a distinct mark on it. How? The key lies in how magnetic fields affect the sea of electrons and protons in the primordial plasma. As this hot, dense soup churned, the charged particles would have been forced to spiral along the invisible lines of a magnetic field. This spiraling motion would have polarized the light scattering off them, imprinting a unique, swirling pattern on the CMB's polarization, a specific type of distortion that is different from the patterns created by inflation or gravitational lensing. It would be a fossilized record of the universe's first magnetic heartbeat. Detecting this signal is like trying to hear a single, pure note played by a violin that has been silent for over 13 billion years. The predicted signal is incredibly weak, buried under the other, stronger patterns in the CMB data. Scientists are meticulously analyzing the polarization maps from observatories like Planck, searching for that telltale swirl that cannot be explained by any other source. What would it mean if we found it? The discovery of primordial magnetic fields would be a revolution. It would tell us that something extraordinary happened in the universe's first fraction of a second, an event powerful enough to generate magnetism on a cosmic scale. This could have been a violent phase transition, a moment when the fundamental forces of nature split from one another, a process predicted by grand unified theories. As the universe cooled and expanded, it might have undergone a sudden shift like water freezing into ice, and the energy released in that cosmic crack-up could have seeded space with these primordial fields. Alternatively, they could have been generated during the chaotic frenzy of inflation itself. Their discovery would open a direct window into an era of physics we can only dream of probing in our laboratories, revealing that the empty space between galaxies is not truly empty, but threaded with the faint, enduring memory of creation's first fierce energies. A second, even more elusive fossil from the Big Bang permeates all of space, a ghostly echo of creation's first second. This is the cosmic neutrino background, a universe-spanning sea of these nearly massless particles, streaming through you and everything around you at nearly the speed of light. Born just 1 second after the Big Bang, when the cosmos was a seething plasma too dense for light to travel freely, these neutrinos were the first particles to break free and stream across the universe. They are the CMB's older, far more aloof sibling. While the CMB gives us a snapshot of the universe at 380,000 years old, the neutrino background captures a moment a million times earlier. The sheer number of these relic neutrinos is staggering. For every proton in the universe, there are roughly 1 billion of them, making them the most abundant particles of matter in existence after photons. Yet their ghostly nature makes them almost impossible to catch. They interact so feebly with normal matter that 1 trillion of them pass through your body every second without a single one ever noticing you are there. So how can we possibly know this cosmic neutrino sea is real if we cannot see it directly? The answer is written in the cosmic microwave background itself. Those neutrinos, despite being so elusive, were a dominant component of the early universe, and their presence had a gravitational effect on the primordial plasma. Think of the early cosmos as a pot of thick soup on a simmering stove. The photons and electrons were the broth, constantly interacting. The neutrinos were like an immense, invisible weight floating in that broth, their sheer numbers and high speeds influencing how the soup sloshed and swirled. This influence left a specific imprint on the patterns of hot and cold spots we see in the CMB. By analyzing the precise statistical properties of these fluctuations, cosmologists can detect the subtle gravitational tug of this neutrino sea. The CMB data tells us not only that the cosmic neutrino background exists, but it also confirms the total number of neutrino species with incredible precision. 3 and only 3, matching the 3 types we have detected in particle accelerators here on Earth. This is a monumental discovery inferred from ancient light, but the ultimate challenge remains a grand prize in experimental physics. No one has ever directly detected a relic neutrino from the Big Bang. Our current technology is utterly incapable of the task. The energy of these ancient neutrinos is so incredibly low that they slip through the entire Earth as if it were not even there. To catch one would require a detector of almost unimaginable scale and sensitivity, a device so massive and quiet it could perhaps be built only on another world, or using the entire planet itself as a component. Why is this direct detection so important? Because capturing just one of these ghostly particles would open a window into the universe's first second of life, a time before the formation of any nuclei, a realm of physics we can never recreate. It could reveal the exact masses of the different neutrino types, a fundamental mystery in particle physics. It might even tell us if neutrinos were part of the process that led to the matter-antimatter asymmetry, the very reason we exist at all. The cosmic neutrino background is the definitive final fossil of the hot Big Bang, a whisper from the moment time began, and its direct capture would be the ultimate act of cosmic archaeology. The shape of space itself might be the ultimate cosmic puzzle. We naturally picture the universe as an endless, three-dimensional void stretching to infinity in all directions. But what if that intuition is wrong? What if the cosmos has a finite, closed shape like the surface of a sphere, but in 3 dimensions? This is the mystery of cosmic topology, the study of the universe's global geometry. The patterns in the cosmic microwave background are our most powerful tool for investigating this profound question. If the universe is finite and has a complex, multi-connected shape, light from the Big Bang would have had multiple paths to travel to reach us. Imagine living in a hall of mirrors where a single object creates an infinite series of reflections. Now scale that up to the entire cosmos. A finite universe with a specific topology, like a 3 torus, would act like a cosmic hall of mirrors. In such a space, if you traveled far enough in a straight line, you would not find an edge. You would eventually return to your starting point from the opposite direction. This would have a direct, observable consequence in the CMB. The ancient light, traveling for billions of years, could wrap around the universe and intersect itself. This would create pairs of perfectly matched circles in the CMB sky, 2 distant circles that show the exact same pattern of hot and cold spots. They would be identical because they are actually 2 different views of the same primordial patch of the universe, seen from different directions after the light has completed 1 or more full laps around the cosmos. Finding even one such pair of circles would be a discovery of monumental importance, proving definitively that our universe is finite and revealing its fundamental shape. Scientists have performed exhaustive computer searches through the CMB data from the Planck satellite, scanning for these telltale cosmic fingerprints. They have looked for circles of all sizes and orientations. The result so far is a profound silence. No convincing pairs of matched circles have been found. This absence is a mystery in its own right. It tells us that if the universe is finite, it must be staggeringly large, far larger than our observable horizon, so large that the matching circles would be too big for us to see or would require a topology more complex than we have yet imagined. The search continues, pushing the limits of our data and algorithms. The question remains wide open, a silent, fundamental query written into the oldest light. Is the cosmos truly infinite, an endless expanse of space and possibility? Or are we living in a vast but ultimately finite structure, a cosmic chamber whose walls are just beyond our sight? The oldest light we can observe brings us to the very threshold of existence, to a wall of fire that marks the limit of our vision. The cosmic microwave background is a fossil from just 380,000 years after the Big Bang, a time that feels impossibly ancient, yet it is an eternity compared to the true beginning. We are peering back through 99.999% of cosmic history, but that final, crucial fraction of a second remains shrouded in absolute mystery. This is the enigma of the initial singularity, the moment of infinite density and temperature from which everything emerged. Our current laws of physics simply break down at this point. The equations of general relativity, which so beautifully describe the expanding universe, predict their own failure, yielding answers that are literally nonsensical when pushed to time zero. It is like using a road map to find your way to the edge of the world, only to have the map turn blank beyond a certain point. The CMB is our most powerful tool for investigating this ultimate frontier. While it does not show us the singularity, it provides the essential boundary conditions for any theory that dares to describe it. The precise temperature and fluctuation patterns we measure are the final outcome of whatever physics operated in that first unimaginable instant. Any viable theory of quantum gravity, any attempt to unite general relativity with quantum mechanics, must be able to start from its own proposed beginning and accurately reproduce the cosmos we see imprinted in the CMB. This is how we test ideas that sound like pure philosophy. String theory, for instance, suggests the fundamental building blocks of reality are not points but tiny, vibrating strings. In its cosmological models, the Big Bang may not have been a true singularity but a violent transition, a bounce from a previous contracting phase. For this to be correct, the physics of that bounce must inevitably lead to the specific pattern of hot and cold spots we observe. Similarly, loop quantum cosmology proposes that the fabric of space itself is woven from discrete, finite loops. This granularity of space would prevent the infinite densities of a singularity, replacing the Big Bang with a big bounce. Again, the CMB data acts as the ultimate referee. Does the pattern of fluctuations generated by a quantum bounce match the real map of the sky? So far, no theory has been definitively confirmed or ruled out. The CMB is a cosmic crib sheet, giving us the final answers to a test whose questions we are still struggling to read. It tells us that our universe is flat. It is made of specific amounts of dark matter and dark energy, and it began with a certain spectrum of primordial ripples. The great challenge for 21st century physics is to write the opening chapter of the cosmic story, the one that leads inexorably to this very specific, beautifully detailed, and deeply mysterious first page. The largest structures in the cosmos were born from the smallest possible vibrations. Every galaxy cluster and vast cosmic void we see today can be traced back to a microscopic quantum jitter, a fleeting tremor in the fabric of reality when the universe was smaller than a single atom. These quantum fluctuations, random and unpredictable at the tiniest of scales, were stretched to astronomical proportions during the universe's first explosive growth spurt. What was once a subatomic hiccup became a gravitational well large enough to trap entire clusters of galaxies. The pattern of hot and cold spots in the cosmic microwave background is the direct, blown-up imprint of this quantum fizz. It is the universe's birth certificate, and it was written in the language of quantum mechanics. This connection between the infinitesimally small and the astronomically large is one of the most profound ideas in all of science. It suggests that the grand architecture of the cosmos was seeded by random, ghostly events that should have been utterly insignificant. The central mystery is the exact mechanism of this incredible magnification. The leading story is cosmic inflation, a period of hyper-expansion that would have acted like a cosmic magnifying glass, taking every tiny quantum ripple and stretching it across the sky. But is this the only story? Could a cyclic universe, one that undergoes endless cycles of expansion and contraction, also plant these quantum seeds? In a cyclic model, the collisions of multidimensional brains could generate the necessary ripples without a singular beginning, offering a very different origin for the cosmic map we observe. The CMB data is the ultimate arbiter between these competing visions of reality. The specific statistical signature of the fluctuations, the subtle way they are distributed, holds the key. So far, the data aligns beautifully with the simplest models of inflation, but it has not yet ruled out all alternatives. The hunt is on for a unique fingerprint in the polarization patterns or the distribution of galaxies that could only be explained by one theory and not the other. The question of how quantum whispers became the blueprint for the cosmos forces us to confront the very nature of reality itself. Was our universe born from a single, inflationary burst, or is it just one page in an infinite cyclical book? The answer is written in the quantum signature of the first light. That first starlight did more than just pierce the cosmic dark, it fundamentally transformed the entire universe. The story of this great transformation is written in the polarization of the cosmic microwave background, a tale known as the epoch of reionization. For hundreds of millions of years after the CMB was released, the cosmos was a vast, silent fog of neutral hydrogen gas. Then the first stars and galaxies ignited, flooding the universe with its first harsh, brilliant light. This intense radiation began to tear apart the neutral hydrogen atoms, stripping away their electrons and turning the fog into a transparent, ionized plasma. The universe was being reborn in light. The CMB carries a memory of this violent transition. As the CMB light traveled through this newly ionized gas, it scattered off the free electrons one last time. This final scattering imprinted a specific, large-scale pattern of polarization onto the ancient light, a ghostly echo of the moment the cosmic fog lifted forever. The great mystery is not that it happened, but how it happened. Was reionization a swift, dramatic event, ignited by a brilliant first generation of immense, short-lived stars? Or was it a slow, drawn-out process, fueled by the gradual accumulation of countless smaller galaxies? The polarization data from the CMB is our most powerful clock for this epoch. By analyzing the precise characteristics of this polarization signal, cosmologists can estimate when reionization began and how long it lasted. Current measurements suggest it was a relatively late and rapid affair, starting around 400 million years after the Big Bang and completing over a several hundred million-year period. Yet the details remain hazy, and the exact nature of those first light sources is one of cosmology's grandest puzzles. Were the first stars monstrous behemoths, hundreds of times the mass of our Sun, burning ferociously and dying young in spectacular supernova? Or did the faint, collective glow from countless small, faint galaxies do the heavy lifting? The answer is crucial because it tells us how the first structures built our modern cosmic world. Next-generation telescopes, both in space and on the ground, are now peering into this twilight era, searching for the faintest, most distant galaxies to see if there were enough of them to power the great reionization. The CMB provides the global timeline, and these deep-field observations provide the suspects. By bringing these two lines of evidence together, we are slowly piecing together the biography of the cosmic dark ages, the moment the universe woke up and saw itself for the very first time. This ancient light has traveled for billions of years on a journey far from straight. As the photons of the cosmic microwave background raced toward us, they did not fly through empty space. They passed by every galaxy cluster, every knot of dark matter, every cosmic structure that had formed by the time they reached it. and each of these massive objects with its immense gravitational pull acted like a lens subtly bending the path of the light. This effect is gravitational lensing, and it has left a faint, swirling fingerprint on the CMB, warping its image like a cosmic funhouse mirror. We cannot see this distortion with our eyes, but through painstaking statistical analysis we can detect it. It is as if we are looking at a beautiful, ancient tapestry through a sheet of wavy, imperfect glass. The glass itself holds a hidden image, the shadowy outline of all the matter in the universe. This lensing map is incredibly powerful. It allows us to see the invisible scaffolding of dark matter, tracing its distribution across cosmic time with breathtaking precision. It is a fossil record of structure formation, confirming that dark matter clumped together first, creating the gravitational wells that ordinary matter would later fall into. Yet, this powerful tool has its own perplexing quirks. When scientists measure the strength of this lensing effect, they find a slight but persistent anomaly. The lensing signal appears to be a bit stronger than what our standard model of cosmology predicts. It is as if the cosmic lens is slightly more powerful, the glass slightly more warped than it should be given the amount of matter we think is out there. This excess lensing is a small mystery with potentially large implications. Does it mean there is more matter in the universe than we have accounted for, perhaps a new, unexpected population of massive neutrinos? Or could it be a sign that dark matter clusters more strongly on large scales than our simulations predict, that its particles interact with each other in ways we have not yet imagined? The most conservative explanation is a subtle systematic error, a miscalibration in our incredibly complex data processing pipelines that is artificially amplifying the signal. But if this anomaly is real, it points toward a crack in our foundational model. It suggests that the cosmic web, the vast, dark architecture of the universe, might be woven with a thread we have not yet discovered. One of the most prominent features in the cosmic microwave background is not a relic from the Big Bang at all, but a signature of our own motion. This is the CMB dipole, a pattern where the sky appears slightly warmer in one direction and cooler in the opposite, as if we are sailing through a gentle cosmic wind. The explanation is straightforward. Our solar system is moving at a brisk 600,000 miles per hour relative to the rest frame of the primordial radiation. It is the ultimate cosmic speedometer, and it confirms a fundamental piece of our cosmic story. But this local motion is just the beginning of a much deeper puzzle. When we correct for our own movement and look at the motions of entire galaxy clusters across the universe, we see something far more strange. These colossal structures, each containing thousands of galaxies, appear to be streaming in a coordinated bulk flow. They are all moving in the same general direction, and this motion persists over distances so vast it should be impossible according to our standard model. This controversial observation has been dubbed the dark flow. Think of it as a cosmic river with galaxy clusters like leaves all drifting in the same current. The problem is, there is no known source for this current within our observable universe. The gravitational pull from all the matter we can see is not nearly strong enough to create such a coordinated motion on such an immense scale. So what could be tugging on entire superclusters of galaxies? One staggering possibility is that the dark flow is evidence of something beyond our cosmic horizon. The observable universe is just a tiny bubble in a potentially infinite multiverse. If another, separate bubble universe existed relatively close to ours in the grand scheme of things, its immense gravitational influence could be reaching across the void, pulling on the matter in our visible cosmos. It would be a ghostly hand from another reality, leaving its mark on the motion of our galaxies. Another, more conservative explanation is that we are misinterpreting the data, that unknown systematic errors or local foreground effects are creating an illusion of a bulk flow. Yet, the signal has persisted through multiple analyses, a tantalizing and unsettling whisper in the data. The dark flow hints that our universe may not be an isolated island, but part of a much larger and more interactive cosmic geography whose full map remains hidden from our view. Perhaps the most unsettling mystery is why these mysteries refuse to go away. Each new satellite, each more powerful telescope, was expected to smooth out the wrinkles in our cosmic map, to finally explain away the cold spot, dissolve the axis of evil, and settle the Hubble tension with cleaner data. Instead, the opposite has happened. The anomalies have persisted and in some cases even grown sharper. This creates a profound psychological and scientific dilemma. Are we witnessing a series of incredibly unlucky statistical flukes, or is the universe trying to tell us that our foundational model is cracked? The standard model of cosmology, lambda CDM, is a triumph of modern science. It describes the evolution of the universe with just a handful of parameters, and it predicts a vast array of observations with stunning accuracy. It is like a master key that has opened countless cosmic locks. But now we are finding locks it does not quite fit, and the more we jiggle the key, the more we worry the lock itself might be different than we thought. The human brain is a pattern recognition machine, and this is both our greatest strength and a potential weakness in cosmology. We are primed to find signals in the noise, to see faces in the clouds. It is entirely possible that these CMB anomalies are just that, cosmic pareidolia, where we are connecting random dots into shapes that are not really there. The sober, conservative approach in science is to assume this is the case until the evidence becomes overwhelming. Yet, the persistence of so many independent anomalies across different datasets makes the fluke explanation feel increasingly strained. It is not just one face in the clouds, it is an entire gallery of them, all seeming to point in the same direction. Could the cold spot, the hemispherical asymmetry, the missing correlations, and the Hubble tension all be separate statistical ghosts? Perhaps, but the haunting possibility is that they are not separate at all, but different symptoms of the same underlying illness in our cosmic model. Maybe lambda CDM, for all its success, is an approximation of a deeper, stranger truth. The real challenge for scientists is navigating this tension between respect for a powerfully successful theory and the obligation to follow the data, no matter how uncomfortable it leads. Do we cling to the elegant model that explains 99% of the universe, or do we start listening to the whispers from that stubborn, unexplained 1%? The persistence of these anomalies is a constant, quiet hum in the background of cosmology, a reminder that our map of reality, however detailed, may still be missing a fundamental feature of the territory. Our cosmic map, for all its intricate detail, marks a final frontier we cannot cross. The cosmic microwave background is a luminous curtain drawn across the universe at 380,000 years old, and behind it lies the true, unfathomable dawn. We can infer the ferocious physics of the first second, but we cannot observe it directly. This light is the ultimate veil, and the final great mystery is what the infant cosmos was like before this curtain rose. Imagine being able to hear the roar of a newborn but being forever barred from the delivery room itself. For those first several 100,000 years, the universe was an opaque, searing plasma, a dense fog of ionized gas where light was constantly absorbed and re-emitted, never traveling more than a short distance before being swallowed again. It is a period forever hidden from our telescopes, a cosmic dark age in the truest sense. Our entire story of the Big Bang is built on extrapolating backwards from the moment this fog cleared. But what if our extrapolation is wrong? The most profound questions of all lie in that hidden era. What triggered the hyper-expansion of inflation, if it even happened? What was the nature of the singularity, or was there one at all? Could our universe have been born from a collision of higher dimensional brains, or from a previous cosmic cycle in an eternal loop? These are not just philosophical musings, they are physical questions whose answers are encoded in the universe's first instance. To peer beyond the CMB, we need new messengers, particles, and waves that escape the primordial fog when light could not. The ghostly cosmic neutrino background is one such messenger, carrying information from just 1 second after the beginning. Capturing even a single one of these relic neutrinos would be like receiving a telegram from a time before the first elements formed. An even more tantalizing prospect is the direct detection of primordial gravitational waves, the ripples in space-time from inflation itself. These waves would have traveled through the opaque plasma completely unimpeded, carrying a pristine record of the universe's violent birth pangs. Finding their unique signature would be like developing a new sense, allowing us to hear the universe's first cry. The next generation of observatories, from space-based gravitational wave detectors to unimaginably sensitive neutrino telescopes, are being designed for this very purpose. They will attempt to pull back that final cosmic curtain to see what lies in the shadows behind the oldest light. The ultimate mystery is not just what we will find there, but whether our current laws of physics can even describe it. The journey to the beginning is the greatest detective story ever told, and the final clues are still waiting to be uncovered. From the grand alignment of the axis of evil to the ghostly pull of dark flow, these 25 mysteries reveal a cosmos far stranger and more wondrous than we ever imagined. We have journeyed from the largest scales of a lopsided universe to the quantum seeds of all existence, from the invisible grip of dark matter to the unsettling tension in the Hubble constant. The cosmic microwave background is not a completed chapter in a textbook. It is a living, breathing document. Each anomaly is a fresh question, a crack in our understanding that invites us to look deeper. This ancient light is a conversation starter from the dawn of time, and we are only just beginning to learn how to listen. The next great revelations are already on the horizon, carried by the James Webb Space Telescopes. Gaze into the first galaxies and the next generation of CMB observatories that will map the primordial whispers with unprecedented clarity. The story of our universe is still being written. Stay curious, follow these discoveries as they unfold, and let us know which of these cosmic puzzles captures your imagination the most. What is your favorite mystery of the cosmos?